Okay, so I thank the organizers for inviting me to this recurring series of events. So it's nice to see many StatMech people. So I'll talk about recent work with my student Dipankar, who is in the audience, and Kaylee Finn, who is a postdoc at Annecy in France. So this is, one of my standard interests. Oh, I should say that this is the archive title, but it has just been published last week in PRE. So this is about my standard interest in exclusion processes. So we found another nice model where we could determine a lot of physical quantities exactly. So before I tell you the model, let me mention a sort of go one step back and tell you about this other model which was solved exactly. So here's the idea. So you have two species of particles in a one-dimensional lattice. The twos are faster than the ones, so they overtake the ones going towards the right with rate 1, and they overtake the ones going to the left with rate q. That's given over here, and zeros you think of as vacancies, so they're empty sites. So you have this dynamics in the bulk, and on the boundary you have this special dynamics where the twos can replace and be replaced by zeros only. So the number of ones in the system is fixed, and therefore this we call this a semi-permeable model, because from the point of view of the ones, they can't escape. They are sort of constrained to lie in the system. So the number of ones is conserved. So for this model, there's a matrix ansatz, which, okay, so there's a typo over here. There should be an E. So what the matrix ansatz tells you is that if you have a configuration given by twos, ones, and zeros, you replace each two by a matrix D, each one by a matrix A, and each zero by a matrix E. And then you can calculate the stationary distribution exactly by taking this product and sandwiching it between these bra and ket vectors. And the point is that you can compute it because they satisfy an explicit algebra. Okay, it's a bit horrible, but the point is it can be done. And this was solved exactly by Professor Uchiyama in 2007. And using quite sophisticated techniques, and I'll mention those in a moment. And that allowed him to compute the phase diagram of this model. And the surprising thing may be that the phase diagram, the parameters for the phase diagram are these very complicated quantities A and B in terms of the boundary parameters alpha, beta, gamma, and delta, and Q. And you have these three regions, A, B, and C. And in each of them, you can, he could explicitly compute the densities and the currents of all the quantities. So we are going to generalize this model. So we call this the left permeable. So for his model, the ones could not leave either on the left or on the right. And what we have instead is, again, similar model. There are three zeros, ones, and twos. Now, and the bulk rules are the same as before. But on the boundary, on the left boundary, the first two rates are the natural rates, in the sense that lower guys can be replaced by larger guys, by bigger guys. But this funny rate is, this funny transition is now allowed, where twos can be replaced by ones. So it sort of goes in the opposite way. But in particular, that these two rates mean that ones can go out of the system. Yeah. Exactly. You mean, yes. So the bulk densities are same. There are some boundary effects. Right. So these are, yeah. So to repeat PK's question, so these are very much analogous to the one-dimensional, single species model that Derrida and et al. Solved exactly. And the phase diagram is similar. So this is the low density phase, the high density phase, and maximal current phase. It's analogous, not exactly the same, because there are two species now, things get a little complicated. So in particular, you have this piecewise constant behavior. So there's some phase segregation phenomenon. Yeah. Okay, so coming back to this model. So this funny transition, this in some sense opposite transition has this rate gamma tilde, and for reasons of exact solvability, that gamma tilde has to be tuned to be this value. And in particular, that means that this alpha plus gamma plus q has to be greater than 1. And on the right boundary, we have the same transitions as before. The 2 is replaced by 0 with rate beta, and the opposite with rate delta. So in particular, what that means for the ones is that ones can enter and exit on the left, but cannot, but they are impervious. I mean, the right boundary is impervious to that. So again, you have a matrix ansatz, this same bulk matrix algebra as before. The boundary algebra is a little more complicated, and this is standard fare. So up to this point, you can do this with many models. The hard part is to find a representation of the algebra. If you don't have a representation, then it becomes extremely hard to calculate anything of interest. And this is where, okay, so before I get to that, so you can do some elementary simplification. You can replace the matrix D by a little d in this way, and similarly for E. And then you find that the matrix A is essentially the commutator of D and E. And then you get a harmonic oscillator type of algebra, slightly Q-deformed version of it, and with certain, again, this boundary vector having certain parameters, in this, which I'm not writing explicitly for just so that you don't get lost in the details. So the point is that this can be solved exactly using some sophisticated methods using of orthogonal polynomials. So there are these. Okay, so we all know the classical orthogonal polynomials, Legendre, Laguerre, etc., Hermite, etc. But there's been a lot of work in the last century, trying to unify all of this. And so in particular, one of these fellows is called the continuous big Q Hermite polynomial. So this is not my terminology, this is there. So it's a mouthful, I know. But these guys are what play the key role here and help us to solve this thing. So Cayley is an expert on these things, so he understood the connection. So just to tell you what these objects are is itself not easy. So you have these Q-shifted factorials. So these are Q versions of Pochhammer symbols, if you like. And so these are various Q products. And then one can define this basic hypergeometric series, which has R parameters upstairs, S parameters downstairs, a Q, and is given in this by this infinite sum over here. Then one defines the specific guy Fn that's of interest for us in terms of these three parameters now, in addition to Q, and a particular specialization of this gives the Q-Hermite problem. It's not that I expect you to understand what's going on, it's just tell you that these are well-defined objects. Then the miraculous thing happens if you set D and E in terms of the standard harmonic oscillator kind of thing that one does. Then the boundary vectors can be written in that basis where the coefficients are exactly the Q-Hermite problem. So that's where life becomes simple. Well, not really, but at least there is some hope for doing something. Then once that stage is set, you can compute various things. So the partition function, okay, you can put some fugacities to count the number of Ds and As, that's 2s and 1s. And then one has this very complicated looking integral formula where theta is an explicit 2 phi 2 hypergeometric series, and this W is the weight. So if you remember, every orthogonal polynomial has is defined with respect, it's orthogonal with respect to what. So there is a weight associated to it. So that's a W. So for example, for your Laguerre polynomials, which are defined on the positive reals, it's the weight is e to the minus x. So this is the analog of that fellow. And theta is some complicated function. So you get this integral representation from which one can then do asymptotics and get various quantities. So the bulk densities and the current are the natural quantities to consider. So these are the densities of ones, densities of twos, and it's not hard to show from the algebra itself that the current of twos is just the ratio of the partition function. So by this I mean ZL evaluated at xi equals zeta equals 1. So then we get an analogous phase diagram where now the parameters for the phase diagram are this quantity B, which is exactly what we had in the semi-permeable ASEP, and this quantity lambda, which is gamma by alpha. And it's very similar to the previous, and we use the same terminology, high density, max current, and low density. And there's a coexistence line where you see shocks. And okay, so these are the densities and currents in each of these phases. So in the max current and high density phase, there's a vanishingly small number of ones. So this is this phenomena we call dynamical expulsion, where even though the parameters allow you to have ones in the system, somehow dynamically they are expelled from the system in these phases. So they exist in a, I mean, they have a density in the other phases. So just to end with some simulation results. So, you know, these are exactly what I said, except for the fact that there is an accumulation of ones towards the end. So there's some right boundary effects in the max current phase. In the low density and high density phase, they are more or less what you would expect. And in the coexistence line, we have this linear density profile in the stationary steady state. But if you take a snapshot of the system, this is what it's going to look like. So there's going to be these shocks, and these shocks are going to have a perform simple symmetric random walks, so that you get this linear profile. So for more details, please see Dipankar's poster, which should be outside. So thank you for your attention.
One question. Okay, so let's thank the speaker again. And next speaker is Pradeep Mohanty.